My name is Jason Duckering, and I will be presenting my research on strength modeling of additively manufactured steel. I'd like to thank Texas A&M's online O-REU program and Los Alamos National Laboratories for sponsoring this project, as well as Dr. Benjamin Efting for mentoring me through the process this summer. The focus of my project is to model the change in mechanical properties between standard grade 91 steel and additively manufactured grade 91 steel. I'll start with some background and why this will be useful to future engineers and research. Next, I'll describe and discuss the different modeling approaches I've taken this summer. First, isostress and isostrain, and then finite element analysis in Ansys. Finally, I'll go over the major takeaways from this summer and make some suggestions for future work on this project. Now on to background. Grade 91 steel was developed in the 1980s to have stable mechanical properties at high temperatures, resistance to creep and radiation damage, and high thermal conductivity for use in critical applications like steam generators, liquid metal reactors, and other thermal power plants. In contrast, additive manufacturing of metals, a process of sintering metal powder into a solid piece to build up complex 3D shapes, has been developed much more recently. This process allows engineers extreme design freedom over conventional manufacturing and machining processes, but the process of sintering successive layers of material together creates a heterogeneous microstructure like we can see on the right, and alters mechanical properties. Prior research took grade 91 steel samples from a standard wrought process and grade 91 samples that were additively manufactured. Half of each group were heat treated to isolate a martensitic microstructure, and the other half of each group to isolate a ferritic microstructure. These samples were all tensile tested to determine yield strength and ultimate tensile strength, to compare results of wrought-based samples with additively manufactured samples. Some of the results can be seen in the figure to the right. X-ray crystallography also determined that the composition of the additively manufactured as deposited microstructure was 15% martensite and 85% ferrite. I will use this data as the inputs to model the effects of additive manufacturing on strength. I started with simple models. Isostress and isostrain models only consider the mass fractions of each component and their individual strength. This approach will give me much clearer direction to continue investigation than more complex models with more variables would. The isostress model assumes that stress is distributed in series as shown on the right, and that each component will be able to elongate based on that stress. This weights the model towards the softer component as it acts like the weakest link. The isostrain model, on the other hand, assumes that both components elongate at the same rate, and the harder or less ductile component will experience proportionally more stress, weighting the isostrain model towards the harder phase. Comparing the results of both models with our observed additively manufactured strength will yield more insightful results than either one would on their own. The results of these isostress and isostrain comparisons can be seen here for the yield and ultimate tensile strengths of the microstructures, the isostress and isostrain models, and the as-deposited additively manufactured strength. The isostress and isostrain models are shown in green and gray, and the blue and orange bars show the strength of the isolated microstructures that were used as inputs for the adjacent models. In each figure, the left side compares models based on standard wrought microstructures to the as-deposited strength, and the right side of each figure compares models based on additively manufactured microstructures to the as-deposited strength. The black bars represent the strength of the as-deposited additively manufactured samples and are duplicated in each figure for comparison. We can see that inputting the additively manufactured microstructures into the models yielded relatively accurate results within 5% of the observed yield strength and ultimate tensile strength. We also see that the wrought ferrite is significantly weaker than the additively manufactured ferrite. This led to less accurate models, resulting in an error between 16 and 18%, which we can see on the left of each figure. One of the assumptions that was made in these models is that the heat treatment was able to isolate the ferrite and martensite phases, and that they would have the same strength in isolation as they do in mixture. The difference between the strength of ferrite based on the manufacturing process indicates that this assumption is likely incorrect. Studies of the grain orientation mapping shows this to be true. A is the as-deposited additively manufactured microstructure, and B and C are the additively manufactured and wrought samples, respectively, that were normalized and tempered to isolate the ferritic phase. We hope to see that the heat treatment was able to create equivalent microstructures from the two manufacturing processes, but we notice significant differences. In B, we can see small uniform grains and no obvious structure remaining from A. In C, though, there are much larger grains and more obvious ferrite lath from the conversion from austenite. These microstructural differences appear to explain the hardening observed in the isostress and isostrain models. Hall-Petch hardening, which increases yield strength as grain size decreases in the additively manufactured samples, is the most likely contributor to this effect. Considering these differences in microstructure, future work may be able to use isostress and isostrain models for rough estimates and quick calculations before using more time-consuming models. Moving on from our initial models, the next approach I investigated was finite element analysis, using Ansys Workbench software to explore the effects of microstructure on the mixing of materials properties. Finite element analysis, or FEA, is a much more accurate way of modeling the stress and strain mapping across complex geometries and assemblies. FEA uses basic static structural formulas and models for mechanical strength, and by automating the process in the computer, Ansys is able to apply these techniques to small sub-elements of larger parts where the behavior is more predictable. And by doing this across the entire part, Ansys can generate much more accurate results for engineers. FEA is not just for complex geometries and engineering stress analysis, though. It can also run studies to simulate standard materials testing like pillar compressions, impact testing, and the loading and unloading tensile test shown on the right. This makes it very useful when exploring the effects of different parameters on material strength. For this project, though, I focused on investigating the two-phase microstructures produced by additively manufacturing. Within Ansys, the user is able to create custom geometries within a single part and assign each element unique mechanical properties, as you can see on the right. This can be incredibly useful when paired with the surface mapping and animation capabilities built into Ansys. It allows the user to see how a load is being distributed throughout a heterogeneous material and explore how different features interact and affect bulk properties. Ansys does come with some limitations, though. It is limited in how accurately the user can replicate materials properties within the software and in how detailed of a model it can handle. The more detailed and complicated the model inputs become, the more likely it will be that Ansys fails while trying to generate a simulation. Ansys does have an extensive built-in library of materials and several techniques a user can use to replicate stress-strain plots in the software, but it still relies on tabular values to approximate stress-strain relations for materials. Barring its limitations, Ansys is still a very useful tool in investigating microstructure and composite structures like the one produced in additively manufacturing. To summarize the conclusions from this summer, I found that Isostress and Isostrain were quite effective models with additively manufactured-based inputs and significantly less accurate with wrought-based inputs. Considering the microstructure differences found in the grain orientation mapping, though, I believe that the difference can be accounted for well enough to use these models for rough estimates before using more complex models. Future work on this project might consider further work with FEA, replicating the strength of the heat-treated samples in Ansys and modeling the additively manufactured microstructures at varying levels of detail to emphasize and investigate the effects of different features. Finally, I want to end by again thanking Texas A&M and my mentor for this summer research opportunity and everything I've been able to learn and accomplish in such a short period of time. Thank you.